Okay, video lesson number 13, solution. So we began this unit by describing the dissolving process, and I gave you what I referred to as the rule of solubility, a general principle that like dissolves like. So one of the most common and known as the universal solvent is water, H2O. If we look closely at water, we know that it has polar covalent bonds, which gives us these partial charges. Remember, the first rule of chemistry is that opposite charges attract. So water will be attracted to things, for example, like ionic solids, because ionic solids have plus and minus charges. So water will be attracted as plus attracts minus. And basically what will happen in this dissolving process is that the water will come in and attack, pull apart, and then surround the solute, in this case salt. Water will also dissolve polar solutes, like, for example, sugar, very well. But when we look at the molecular level and we try to put oil in water, that does not dissolve. Notice that in this case, the water has nothing to attract itself to the oil. The water actually is attracted to itself. So when we looked at that, right, I gave you this example, the oil and the water, they don't form a solution. Okay. The other one, which we looked at, for example, was the sugar water or the Kool-Aid, right? That does form a solution as like dissolves like. Now, I'd like to show you the dissolving process using our PHET or PhET simulation from the University of Colorado at Boulder. That really just shows you in some good detail, and we looked at that, and you're welcome to look at that more on the internet, free of charge, thanks to them. Okay, here we are looking at water, which is my solvent, and then I have two solutes, salt and sugar. So remember, the solute is the thing that gets dissolved, the solvent is the thing that does the dissolving. So notice what happens when I put my ionic crystal lattice of salt into the water. The water is attracted plus and minus to my salt, and the water attacks, separates, and surrounds the salt. Now notice here it breaks it into ions, and we said and showed in a other simulation over here, right? When I put my salt in here, because it breaks into ions, it does conduct an electric current. Okay. Now, I can also look at water dissolving a covalent substance like sugar. Okay. So in this case, the water attacks and surrounds the sugar, but notice that the sugar does not break apart into ions. So the sugar is dissolved, but because it doesn't break into ions, when I go back to this tab and I reset all and switch this to sugar, and we looked at that, right? And I brought my conductivity apparatus in, notice it does not conduct an electrical current. Okay, then we looked at factors that affect the dissolving process, and we broke those into two categories. The first category is how much solute will dissolve. So how much solute will dissolve in the solvent really depends on three things. Number one is the type of solute and solvent. And so I gave you the rule of solubility, like dissolves like. We're referring to the charges or lack of charges thereof and the type of that are due to the type of bonds, polar covalent, nonpolar covalent, ionic, etc. The second thing we looked at was temperature. So temperature will also affect the amount of solute dissolved. For solids, remember, an increase in temperature increases the solubility, and we'll look at the solubility curve of different solids here in a second. And then we also looked at gases. Remember, for gases, that effect is opposite. Increase in temperature actually decreases the solubility of gases. Okay? And then lastly, we looked at pressure. Of course, pressure affects only gases, and that can increase the solubility if you add pressure, pushing the gas into solution. Okay? And then we also quickly reviewed factors that affect the rate or the speed or how fast something dissolves, and I referred you to the kitchen where there were a number of examples that we went through. Okay? Of course, heating something up will increase the dissolving process. If we think through what that looks like, more motion, more kinetic energy gives me more motion. More motion means more interaction between my solute and solvent. I'm going to get faster, more dissolving over time or a faster rate. Okay? Same thing with stirring without adding the energy or heat. More motion, more dissolving, and then also surface area. If I increase the surface area, that gives me more areas to contact. That will also make my dissolving process go faster. All right. Now, we then looked at solubility curves, and so I wanted to just do a couple of examples with you just to kind of think through. Now, always the temperature is on the x-axis. That's usually in degrees Celsius. On the y-axis, we have solubility, which is in grams of solute per 100 mils or 100 grams of water. So this one's a simple curve because there's only 3 things, so we can keep that straight. So I thought we'd go through a few questions together. Question number 1 says, which salt is most soluble at 80 degrees? So to answer that, what I do is I take my pen, or in my mind, I go to 80 degrees, and then I go up, and I look at what would be the most dissolving happening, okay? And in this case, the answer would be potassium nitrate, okay? Because it's the highest line. Question number 2, how many grams of potassium nitrate can be dissolved in 100 mils of water at 50 degrees? So again, don't be afraid of the wording of the question. Usually 100 mils of water is the baseline in terms of what the curve actually shows me. So I just simply go to 50 degrees and I find potassium nitrate, which again is that same blue line. And then I go over to my y-axis and extrapolate over. You can see that I would get 80 grams of potassium nitrate at 50 degrees. Okay? So that's the typical question. They might throw one at you like this, number 3, where we now ask how many grams of potassium nitrate can be dissolved in 300 milliliters, or 300 milliliters of water at 50 degrees. So remember, 100 was 80. I basically am tripling my solvent, so I can triple my solute. So the answer would be 240 grams. If you wanted to, we could set up a proportion. So we could do 80 is to, that's 80 grams to 100 mils, as X grams is to 300 mils, okay? Something like that. Cross multiply and solve for X, we will get 240 grams, okay? Question number 4, if 80 grams of sodium nitrate is dissolved in 100 mils of water at 30 degrees, is the solution saturated or unsaturated? So thinking about those vocabulary terms, remember saturated means it's at the max, unsaturated means we're below the max. So I simply need to go to 30 degrees and then find sodium nitrate. So here's 30 degrees, sodium nitrate is this line right here, okay? And then I extrapolate over and I look and say, okay, what do we got there? So if I have, how much can it hold? It looks like I can hold over 80 grams, so like maybe 82, 85, depending on how I mark the curve. So if I've got 80 grams, okay, and it can hold 82 or 85 grams, clearly I am below that max. So in this case, my answer would be unsaturated. Okay, then lastly, and the trickiest of them, number 5, we have a saturated solution of sodium nitrate formed in 100 mils of water at 60 degrees, and then it's cooled to 20 degrees. How many grams of precipitate are formed? So basically what I need to do is figure out how much is it holding at 60 degrees Celsius. So I find sodium nitrate, again that's, and I find 60 degrees. So 60 degrees is right here. I go up, I have about 120 grams, okay? So at 60 degrees, I can think about this. I've got 120 grams, okay? And then at 20 degrees, I'm just boxing this off so you know I'm not dividing it. I figure out how much it can hold at 20 degrees. So if I go to 20 degrees and go up, it can hold 80 grams, okay? So I'm at 20 degrees, so all it can hold is the 80 grams. Now, I have 120 grams in there. So basically, my solution will precipitate out the difference of 120 and 80, which is 40 grams. So my answer here would be 40 grams will precipitate out as I subtract those. Okay, and then finally we talked about how to calculate the concentration of a solution. Now the concentration is the amount of solute in a given amount of solvent. So think about it that way, solute in solvent. That will help us out with the calculation. So there's 3 main ways to, or at least we talked about showing the concentration or calculating it. The first and probably the most important is molarity. Molarity is the number of moles of solute per liter. So mole solute per liter solution. We also looked at grams per liter, which is the number of grams of solute per liter of solution. And then lastly, or finally, we looked at percent composition. Percent composition is a gram solute divided by gram solution. times 100%. So that'll give me a decimal. I times it by 100%, I'll get a percentage. We can also do percent composition by volume as well. So let's look at 3 examples real quick. The first example, it says a solution containing 5 grams of sodium hydrogen carbonate or baking soda in 25 mils of solution. That's what I've got. Calculate the concentration in grams per liter. Okay, so I want to think about how much solute and how much solvent. I've got 5 grams, and I've got how much solution or solvent. I've got 25 mils. So notice here, that's grams per milliliter. But what I want is grams per liter. So if I thought about that, using my T-chart and my dimensional analysis, grams are on top, that's good. But what I want is liters on the bottom. Right now I've got milliliters. So I've got to get rid of milliliters, okay, by putting it on top, and then I want liters on the bottom. Now, assuming that I know how many milliliters are in a liter, then I can use this tool. Notice milliliters would cancel, and I'll get grams per liter for my unit. And of course, I know that 1 liter is 1,000 milliliters. So then I can just multiply on the 5 times 1,000 on my calculator divided by 25. I'm going to cancel 5 out of here. So really I get 1,000 divided by 5, which would be 200 grams per liter. Okay. Example 2, it asks how many grams of sodium hydroxide, or NaOH, is needed to make 1 liter of a 0.5 molar solution. Now, what you need to recognize is the capital M. That means molar or moles per liter. So that's the molarity. So with these, you can start wherever you want. You can start with the 1 liter or the 0.5 moles per liter. I typically will start with 1 liter here, and then I want to think about what I want. What do I want to get here? The question is asking how many grams, right? So I've got to figure out how many grams. That's going to go over here for my target, okay? So how am I going to get liters to get into mass? Well, really the molarity is my conversion tool, because what is molarity? It's the number of moles per liter, okay? So notice that my liters would cancel. That would give me moles, and of course I can remember back to my molar mass, right? Grams per mole. I can put moles down here, grams here, and now all my units make sense. I just got to go back and plug in my numbers. Okay. So the molarity was 0.5 moles. Again, that's always per 1 liter. And then I just need to know now the molarity of my sodium hydroxide to get this gram sodium hydroxide. That's the molar mass. So I look on the periodic table. Sodium has a mass of 23 grams per mole. Oxygen has a mass of 16. And hydrogen 1. If I add that all together, of course, that gives me 40. And so my answer here would be 0.5 times 40, or 20 grams of sodium hydroxide. So if I wanted to make 1 liter of a 0.5 molar solution, okay, I would need 20 grams of sodium hydroxide. Last example here, percent composition. It says, what's the percent composition of a solution made with 50 grams of sodium chloride in 150 mils of water? Now, the only thing tricky here is, remember that percent composition is the grams of solute divided by the grams of solution, okay? So you got to be careful, because it may or may not say solution here. In this case, it doesn't. It says 150 mils of water. So if you imagine it like this, if I have 150 mils of water, then I add 50 grams of my salt, how much solution do I have? Is it 150 or is it 200? Well, there was 150 grams right here, right? Plus 50, that gives me a total of 200 grams of solution. Okay, so you have to be careful. If it says water here, you have to add the solute to the total. Okay, if it says solution, then you don't. So you have to read it carefully. So the calculation is fairly simple after that. It's just 50 grams. Okay, and again, I would divide that by 50 plus my 150, so it would be 200 grams times 100%. Okay. So I could do that on my calculator, or I could just cancel, right? That goes in there, 5 goes into here, 4, so it's just 1/4. I know 1/4 is 0.25 as a decimal, times 100%. That gives me a percent composition of 25%. Okay, so again, I hope that was helpful. Keep practicing. I'll see you in class.